Hello class, in this video we'll continue our lecture from last week on integers, and apologize if I cough a little bit throughout the videos, but my throat is a little bit scratchy and my voice is a little strained, but I think I will be able to make it. But anyways, so last week we talked about the integers as being the set of both positive and negative whole numbers including 0. So we talked a lot about the necessity for negatives on the conceptual side, where a lot of times, one of the examples that I like to use is, say we're talking about a comparison between someone who's 7 feet tall and 5 feet tall. The 7-foot person is, of course, 2 feet taller than the 5-foot person. But if we reverse the comparison, if we compare the 5-foot person to the 7-foot person and subtract the other way, we could say that the 5-foot person is 2 foot shorter. And, being both taller or shorter, a positive or negative value can be assigned to the comparison based on the reverse order of subtraction. Because as we know, subtraction is not commutative, but the answer that we get has the same absolute value. And the absolute value is just the raw value of the number, regardless of positive or negative. But one thing that can be very helpful when thinking about negative symbol, because again, the negative numbers are not the same as subtraction. That's another key difference. Is really there's three different conceptions of what a negative sign or symbol, the minus sign, means on a mathematical expression. So it could mean subtraction, such as, if we have 4 minus 6. Whoops, don't want to be using the highlighter. Say we have 4 minus 6. Whoops, still using the wrong thing. Cool. Erase that. All right, sorry about that. 4 minus 6. Or we could just have -2, where again, you could write it as a small negative above the number, or just look like a normal -2. It's different. And the thing we were talking about towards the end of class is these are not the same thing. It's the same symbol, can be confusing, but subtraction is different from a negative number. Where of course those answers, these are equivalent expressions, so it's not so much different, but it has a different meaning. And the third meaning of a negative symbol is just being the opposite of. Because again, thinking about a negative number, we could think about it as the opposite of a positive number. But say we're considering the idea of what a double negative means, as we were discussing. As we know, 2 negatives make a positive. But the reason is because the negative always means an opposite. And if we have the opposite of an opposite, it's the original thing to begin with. Because a negative number, the opposite of a negative, is a positive. And so the reason why 2 negatives make a positive is because of this conception of an opposite. But if you don't establish all 3 meanings of what negatives are and their entire purpose, a lot of those rules will not make sense to your kids. And again, for me, I remember learning the rules and I was just sort of went along with it. I'm like, okay, I'm sure my teacher's not lying to me, but a lot of kids will wonder why. And they, sometimes they won't even ask. So it's important to try to be able to explain these things. And the third conception is one that is often missed. And a lot of students don't really get the differentiation between subtraction and negatives as well. They sort of figure it out as they get older. At least that was my experience. But they all kind of play into the same idea. And I think I forgot to mention this, but actually subtraction to begin with is the opposite of addition. So really the opposite idea encapsulates all of those ideas together, because the opposite of a positive is a negative. And that's kind of what we mean when we write negative. And the opposite of addition is subtraction, which is why, it feels into that opposite flavor of things. But let's say we actually have negative numbers and we want to add or subtract them. That's kind of what we're going to be moving into next. But let me go back to the slides because I don't want to forget any important things. But integer operations, and again, when I say integers, what I always think of is negatives, because students already know how to, the assumption is they already know how to do the basic arithmetic, adding, subtracting, multiplying, dividing with positive numbers. Now we throw negative numbers into the mix, it can change things a little bit, and there's some new rules that they have to learn. But often the minus sign is not really well established or understood because the students already know what subtraction is. They already have been using the symbol. But now when we start using negatives, it can be very strange to be reusing the same symbol for a new idea, and that will cause problems, especially if you start getting into the algebra side where you talk about double negatives and so on, multiplying negatives. Again, we're going to get into that. But essentially, a lot of times we can help our students to understand by using manipulatives or by using conceptual methods, like base blocks and so on. But with negatives, there's, with base blocks, you could use like red base blocks for negatives and green for positive or something. But usually that's you then would have to get a whole bunch of different base blocks of different colors. But typically, number line is a very useful way of doing it because the number line can describe both the positive and negative direction of numbers, and I'll be using that from time to time as we already have been. But the chip model is another one which can be very, very helpful. It's sort of like a simplification of using colorized base blocks. But let's look at an example. So say we're using the chip model to describe numbers, right? The black chips represent positives. Again, you can use green if you want. And the red chips are going to represent negatives. So say, for example, we have a positive 2 that's could be represented by obtaining 2 black chips. And if we have a negative 2, we just have different chips of red color instead. And the point is we're distinguishing positives from negatives, whereas 2 is the absolute value, the raw number of them. And if the students, this can be confusing because they wonder what's the difference, why does the color matter? But essentially, if you've kind of established the idea that positive numbers are like something we have. I like the debt example a lot. If I have $2, this is a positive number. If I owe someone $2, that's a debt, and that's something that I will have to pay off later. And that helps me distinguish between the two numbers in terms of what they mean. But if we start combining the chips, those can also equate to an overall. Like say I have $3 and I owe my friend $1. That's a total value of a $2. And essentially red and black chips cancel each other out. So you can have your students draw the numbers in terms of canceling them out. And this is very helpful with addition. So let's go back to the packet and look at these examples. But when adding integers, like there's a couple strategies that I like to use, and essentially, boiling back down to the most basic conception of addition and subtraction, addition is combining or joining together, where subtraction is take away. And we can use those ideas with the chip model to think about why these things will happen. So let's start off with some of these examples, but addition means combining. And so, let's say we wanted to do 4 plus a negative 3. Again, you guys probably remember how to do these things in the rules. There are rules specifically for positives and negatives. I'm trying to not focus on the rules and thinking about why and if we're trying to use a conceptual model. But essentially, let's say we were using the chip model because I kind of like that one the best. Well, so what we have is 4 positives, right? Because if there is no number, again, we could write this as plus 4, but that we have 4 positive chips, 4 black chips, and we're adding 3 negative chips. So basically, let me draw 3 red chips as well, because we're combining all of those things together in our chip model. And if we look at the net result and we cancel, because every dollar can be used to pay off a debt, right? And I can kind of cancel out the common values. What I end up with is a value of 1, and that's again going to be the answer in this case. 4 plus negative 3 is equal to 1. Now again, most kids learn how to do this by just saying, well, adding a negative is the same as subtracting, which is true, it is, but it can make a lot more sense if we're combining a debt with a positive, right? Debts and positive cancel each other out. So adding a negative is effectively like subtraction, which is essentially the rule. And in the rule, we have some rules which will come to kind of a generalization in the number theory or algebraic side, as our book always likes to do, to bring it back to the set theory, mathematical theory of the subject. But say a similar example, say we had 3 plus negative 7. Again, we could draw those two numbers because again, if we're adding, that means combining. So I start with 3, and then I have 7 negatives. 1, 2, 3, 4, 5, 6, 7. And every positive and negative will cancel each other out, because I could pay off a debt, leaving me with 0. But of course, in this case, if I have 3 positives and 7 negatives, and I combine all this together, I'm going to be left with negative 4 again as the answer to the sum of a positive with a negative. And notice that if I switch which one is if I switch the add-ins around, we know addition is commutative. Now, the commutativity of addition works with integers as well. It works for addition, generally speaking, unlike subtraction. So technically, we could think of these problems as the same. And if we're thinking about, well, why is addition, including with negatives, commutative? Well, if I'm joining 2 objects, it does not matter which one I draw first. Because really, well, I start with negative 5. I could draw the negatives first, then draw the positives. Notice that makes no difference, right? Because ultimately, I'm joining those things together. and all 5 of those will cancel each other out. So in this case, we're going to get 0, and we get the additive identity of the integers, because there is always the additive property of 0 is what I mean. But there's always a number. When we're talking about whole numbers, there was no way to make 0 with addition, because if we're only adding positives, you can't add them together to make 0. But when you're working with negatives, you can add 2 numbers together to get 0. And again, of course, the same number, both positive and negative, will cancel each other out. Another basic mathematical principle that is easy to demonstrate once we've established the idea of negatives and using the chip model. Now, the number line model is another one which is quite useful. And so let's say we're starting with the number line. And what helps with the number line is just to remember that it's directional, where positive direction is one way and the negative direction is another way. As I illustrated in class, this could make sense, because we could imagine, say I'm trying to go over here. This is, work or school, and we're trying to go in the positive direction. We're trying to get to where we're going. If we go the wrong way, it's actually being harmful. If we walk backwards, we're going in the negative direction. It's kind of harmful to our progress in that case. And we could think of positive numbers as traveling the correct way or to the right, and negative numbers as going to the left. And technically, the fact that negatives are on the left is totally arbitrary. Mathematically speaking, negative does not have to be the left. It's just a well-established. It's kind of like we read from left to right. Everything is done on a right-handed way. There was a lot of right-handed bias, or in early education, where right-handedness was thought to be good and left-handedness was thought to be evil. And as we know, that's completely ridiculous. But I think that's why, you can often make the heaven and hell argument, where up is good, heaven, down is bad, negative, right is good, left is bad. Again, negatives aren't necessarily bad. If we're thinking about them in terms of debts, they're bad. You don't want to be in debt, but, it's always the opposite nature. One way is positive. The other way is the opposite. It's the negative way. Anyways, but if I start with a positive, when we're adding, we always start with one of our numbers, the first add-in, and then we need to add the second. But the thing is that I need to remember, if I'm adding negatives, I just need to go the wrong way, because I'm, adding in a negative direction. So I'm going to end up going backwards 3 units, because that is equal to adding a negative 3. And I'm going to end up at 1 if I started at 4 and move backwards by 3. Just like as if I added positive 3, I'm going to go the correct direction, and I'm going to get to 7 instead. But the number line, very helpful. Another way of establishing the idea of directionality. So in the next video, let's get into subtraction. This one's getting a little too long.